100th bite of physics. And in honor of that particular milestone, we have our first guest presenter who is not Ben Tristram. Ben's taken a lot of bites when I have not been available. But today we actually have somebody who's going to be a guest presenter. I'm going to sit here and read the chat and listen to her talk. And that's a particularly special guest presenter for me. Um, yeah, anyway, my wife really would like to hear this, but she's not going to be able to, unfortunately. Uh, we may work on that. Anyway, let me just say a few things about this. In the scientific discourse house, as a lot of you know, we generally talk about interesting aspects, but of well-established physics. We don't talk about cutting-edge things. We don't usually don't talk about current research. And we're aimed at non-scientists, but at a level a skosh higher than usual. We'll talk about an interesting little aspect of well-known, well-established physics that can be kind of dealt with at a little higher level to give you a little taste of what a higher level looks like. Today, we're stepping out a little because we're having an active research scientist talking about a research program that involves unusual travel opportunities, awesome scenery, important geology, timely geology, and more physics than you might at first imagine. She's going to talk a little bit about isotopes, cosmic rays, and things like that as well. I think you'll find the presentation not only accessible, but exciting and visually amazing. She's prepared a lot of slides, most of which are pictures that I think she'll go through. She knows she will try to kind of make her presentation about 45 minutes to an hour, and then take a few questions. But she has to hit the road, so she's not going to be around for long. At least I hope she know. Hope she gets out of here and hits the road. Claire grew up in Atlanta, Georgia, one of five daughters of college friends of my wife. And then she came to Claremont for her undergraduate work at Claremont McKenna College. Both the town and the college, amazingly enough, were subsequently named after her. Kidding. After graduating from CMC, she went on to get a master's, I think, in environmental engineering. I think that was the name. Claire, why don't you chime in? Why don't you chime in here? Introduce yourself, and or at least introduce your voice.
Yeah, hi everyone. This is Claire Todd. I'm really excited to join your discourse today and share a little bit about my research in Antarctica. So yeah, John, you're right. It was actually I think a master's technically in Earth Resources Engineering, but certainly under
Oh,
the
okay,
environmental umbrella. So
that's right. And then so that was at Columbia, and then she went to University of Washington, where she got her PhD in geological sciences, maybe Earth. I don't know what the name of the department there is. But she had recently came down south from Seattle, so she's now a neighbor, and she is now chairing. She's a professor and chair of the geological sciences department at Cal State University San Bernardino. During her summers there, she conducts glacial research still up on Mount Rainier. She takes students, she handpicks a few students every year, takes them up to Mount Rainier, and they climb up the mountain and do some geology research up there. But most importantly, she's a veteran of six field seasons in Antarctica. There may be some people here who want to ask her whether there's actually a 24-hour sun in Antarctica, but I hope we don't spend too much time answering that question. Claire, in fact, has never seen the sun set in all of the time, and she spent probably, I would guess, probably close to 6 months now, 4 months at least in Antarctica. She's never seen the sun set there, which is kind of interesting. She studies glacial retreat, and I think she's led the last three expeditions. Is that right, Claire?
yeah, certainly the last one I was the solo lead, and then on the previous two I was part of a leadership team.
Yeah. Anyway, this is going to be an awesome talk. Claire and her husband George throw simply awesome parties. You should know that as well. She joined Clubhouse yesterday, and she's already mastered that mic button. So, anyway, we'll get back to Claire in a second here. Let's welcome my other usuals on stage and encourage anybody who wants, raise your hand. We'll bring you up as well. Um, we have Shamash, aka Logic Guy, who is, I think, probably by now streaming simultaneously to YouTube. So this is also on YouTube Live, and it'll be collected in the scientific discourse section there. Claire probably didn't know that. Hey, Shamash.
Hello, hello, and so happy to be here to witness this special event, 100 bytes of physics. Maybe we can talk about that towards the end, not to dwell on it a lot. But I want to welcome Claire as well. We all know you here. I'm not sure if you know that, but we know your news, we know your stories, we know everything about you, right? John hasn't saved any effort telling us everything about you, so we are very excited to have you here.
Yeah, some of you know I refer to Claire all the time. Go ahead, Claire.
I was just going to say thank you. That I'm sure it's unwarranted attention, but I'm very happy to be joining you all. I've certainly heard a lot about this group and how much it means to John. So the mutual respect is felt all around. So thanks very much.
Claire, most of you know I refer to her all the time as our sort of daughter because, as I said, she's one of five daughters of my wife's college friends. We didn't have any daughters; they had five, so we kind of feel like we should at least get one of them. So I refer to her all the time as that, and I take great pride. The great thing about her being my sort of daughter is I can be really proud of her, unlike her real parents, who would have to be a little embarrassed when you're proud of your own daughter. We take a complete pride in her because I had nothing to do with it. So
Just a
that's
quick
where we
question
are. Hmm?
for the sake of the stream. Am I following Claire's lead on the slides, or are you, John, flipping the slides? Who has the lead?
Oh,
I have the
well,
lead.
so she'll be describing them. I think that's the yeah. You should follow her lead on what
All right,
slide
cool.
she's talking about. Yeah. But everybody, of course, should open it if you can to follow along. I know that's sometimes difficult, but these are beautiful slides, so you really want to do that. So let's hurry through the rest so we can get to the talk. I'm going to go to Sam here first, one of the co-founder of the Scientific Discourse House. Hey, Sam.
Hi guys, hope everybody's doing well. Welcome Claire to Clubhouse and to Scientific Discourse. We're looking forward to enjoying your presentation.
Thanks,
Thank
Sam.
you.
And Andy, hero protagonist. Good to see you, Andy.
Good morning, and nice to meet you, Clark. Thanks for being here.
All right, and we have a couple other folks on stage. Benjamin, who's quite. I won't go to Benjamin first. I'll say hi to Bert. He's been here longer. Bert doesn't always join us, but Bert is an optical guy at NASA Goddard. Good to see you, Bert.
Good to see you, but there's an asterisk after that that I have taken the early retirement.
Oh, I didn't know that. Okay, you were a
Uh
former optical guy at NASA Goddard.
huh. I'm freelance now, which gives me more time on Friday afternoons to join in.
All right. And finally, Benjamin. Now, Benjamin, know that I've warned Claire about you, but maybe you want to say hi quickly.
The guy your dad warned you about.
All right. So anyway, maybe without any further ado, let's let's see. Wait a minute. What? Just one more further ado. Let's see. Where's that? There. It's in there. Okay. So let's all welcome Claire and thank you very much.
Welcome,
Yes.
Claire.
Okay. So take it away, Claire.
Thanks, John, and thanks everyone. Certainly a very, very generous introduction, and again, really glad to join your group today and to talk about some of my work. And also, as soon as I figure out how to make all those emojis circle around your pictures, I'll join in the fun there. But I definitely appreciate the interaction already, and you should feel free to interrupt me at any time. I do. It is a slide-based talk, but I'll do my best to talk you through it, even if you're not able to pull the slides up. And without further ado, let's go. So the main focus, or I'm on slide 2 now, the main focus of my work is tracking how the Antarctic ice sheet has changed across thousands of years. And I always bring students with me for these, or at least for the more recent seasons. And those students are sort of an active part of the research team and collecting the samples and making the maps that we use as part of our research. And as John mentioned, I'm at Cal State San Bernardino, where I chair the department and am professor as well. So I think a key thing before I go on, I'm on slide 3 now, is that I put an asterisk after my name as author because this kind of research happens in collaboration. There's no way that I could do this by myself, and so I collaborate with people across the country. The most recent project with Dr. Greg Balco, Dr. Seth Campbell, Dr. Ryan Venturelli, and a mountain guide named Danny Ullman, who's from the States but based in Chamonix. And it also requires funding. So all of this is funded by the National Science Foundation, who runs the United States Antarctic Program, and it's a team effort. It requires years of planning, submitting proposals, and they go through a rigorous scientific and then logistics review. So this is not my own work. This is really only possible because of the contributions of many people and of federal funding. So I've shown some pictures of my most recent student participants. And you'll see some more pictures of them going forward. Um, so just to give you a quick outline of the talk, I'm on slide 4 now. I'm just going to give you a little bit of background about Antarctica. I'm sure for some of you this will be obvious, but I think it's always good to sort of lay the groundwork, make sure everyone knows where I'm talking about. I'll describe how to get there, how we actually access our field sites, and share with you just a few of the observations of ice sheet change that we've made, how we determine when the Antarctic ice sheet was where in the past, how we actually date that process, and then just give you some brief take home points, some example results from what we can say based on that. So I'll stop there and just see if there's anyone who has any questions right off the bat. And I'm not as
Claire,
adept.
nobody will
Yeah,
ask you
go ahead.
questions here except for me. That's just how this goes.
Okay. All right, go ahead.
I I think it might be just a little bit too early to ask the questions, and I don't want to get
Yeah,
into the funny questions. So maybe we should just keep going.
Okay.
yeah, I think that's fine. I think maybe the best thing is, Claire, when you think you're at a place where there might be, go ahead and do that. Otherwise, people I think should feel free to kind of unmute and say question, and then I think Claire will accommodate you.
That sounds great. Yeah, happy to be interrupted. So thanks to you both for sharing that guidance. I appreciate it. So you may have heard about Antarctica in the news. On slides 5 and 6, I give just a few examples of the types of headlines that you might have read about Antarctica. Antarctica is melting and we all need to adapt. From an article a couple of years ago, rapid melting in West Antarctica is unavoidable with potentially disastrous consequences for sea level rise, study finds. On slide 6, melting Antarctic ice will raise sea level by 2.5 meters, even if Paris climate goals are met. So these are the types of things that people read about in the news. There's a particular glacier, in fact, that has received a lot of attention lately, the Thwaites Glacier, which is a large glacier in West Antarctica that is thought to be melting quite quickly. And that mass loss has actually been measured directly by satellites and other methods. So when you hear about Antarctica in the news, it's often with a lot of sort of tracking very recent change and the rate at which that change happens. And my work is actually about the longer term change on the continent. How quickly does the ice sheet retreat or thin over much longer periods of time to provide context for these types of changes that have been measured over more recent time periods. So Antarctica 101 on slide 7, just to orient everyone, we're talking about the South Pole. Some of my students sometimes when I first start talking about Antarctica, they confuse it with the Arctic. Very different place. There's no continent in the Arctic Ocean, but Antarctica is a continent. It is basically, if you peeled all of the ice sheet away, you would find basically submerged marine basins and archipelagos, chains of islands. But it is, in fact, the seventh continent, as we know. It extends from about 66 degrees south latitude all the way to the South Pole. Contains two ice sheets, West Antarctica and East Antarctica. And it is about the size of the continental United States, the lower 48. Those are approximately the same geographic size. So what exactly is it when I'm saying an ice sheet? On slide 8, I show you a digital elevation model of the ice sheet. This is basically satellites measure the elevation of the ice sheet and then a map is created where the different pixels on the map are colored to represent the elevation. So for those of you who are able to see the slide, you see dark blue colors over East Antarctica, representing higher elevations, 4,000 meters or so. The South Pole, for example, is at 10,000 feet. West Antarctica is not quite as high elevation in its center, but it is a continent-sized sheet of flowing ice. It flows because gravity is acting on it on a slope. And so we see basically ice flowing from these higher central elevations over 10,000 feet in East Antarctica, ice flowing from those central high points out to the margins, of course, to sea level. So you can think of it as a continent of ice flowing over mountains, sometimes through mountains. And for a geologist, you have to work hard to find field sites. I know that less than 1% of the continent is exposed rock. So if you're a geologist, you're limited to where you can go. I've shown you some of the locations of my field sites, and I'm going to focus. I'll show you pictures from sort of all of the places that we have been. Any questions about sort of the ice sheet component of Antarctica?
I was just going to say one quick thing, Claire, is that I only kind of recently understood. I always had a trouble with West and East Antarctica, and it's nice to kind of appreciate that the small part from that archipelago that reaches up towards South America to the bay that McMurdo is in, that kind of defines West Antarctica, and it opens up toward the Pacific Ocean, right? It's the West in that sense, and that was a revelation for me to kind of realize I could understand it that way.
Oh, excellent. That's helpful. Yeah, and Eastern and Western hemispheres. Yeah, all of that is helpful. It is certainly maps and everything there is, mapped on a polar projection. If you want to know which way, basically everything is south or north, I guess, depending on your orientation. But certainly the orienting yourself down there is um, a different prospect than when you are closer to lower latitudes. So. And why does it matter? So on slide 9, I'm going to show you first an image of ice thickness. So I've told you that the center of East and West Antarctica are those are the highest elevations of the ice surface. That is also where we find the thickest ice, in some places over 4 kilometers thick. Um, and that ice, critically, is resting in a basin below sea level, in some places 2 kilometers below sea level. So we have really thick ice sitting in effectively a bowl in some places, and the bottom of that bowl is below sea level. And that sort of brings us back to some of the headlines that I first, we're on slide 10. That's bringing us back to some of the headlines that I first shared with you. That ice perched below sea level, large volume of ice perched below sea level, has been referred to as the weak underbelly, particularly of West Antarctica. And so on slide 11, there's just a little bit of a cartoon from NASA illustrating how the ocean, particularly sort of warmer ocean waters, can access that supposed weak underbelly and flow into submarine basins that might then accelerate the mass loss of the ice sheet. And there's potential for many meters of global sea level rise, depending on which chunk of the ice sheet you model melting into the oceans. It's several meters of sea level rise in West Antarctica, and many more meters depending on which model you use for East Antarctica. So while total collapse of the ice sheets is not thought to be in our near future, nevertheless, it represents a reservoir of water that has the potential to raise sea level significantly. And we know that there is a mechanism for that to happen. We're measuring it happening in real time. And there are a lot of numerical models that also try to track how those mechanisms might evolve in time with a warming ocean and increasing sea level rise. So I hope that gives you enough motivation to start to be curious about, well, how does this thing change? How does the ice sheet change? That global sea level rise will impact all of us at some point. On slide 12, as part of sort of my why does it matter section, I've shown you this a map from NOAA's Sea Level Rise Viewer. The National Oceanic and Atmospheric Administration has a website, a Sea Level Rise Viewer, where you can look at your location and see how your particular coastline might be affected by sea level rise. And so this is just showing you basically current coastal flooding areas that are not thought now to be subjected to high potentially like raising sea level. Oh yeah, Miami is uh has challenges ahead, that's for sure. And you can see also in the Bay Area there are a lot of low-lying areas, and so I'm not going to activate the sea level rise viewer right now. You can do that on your own time. I've linked it in the slides, but you can go to different dashboards in the sea level rise viewer and raise sea level to your sort of choice to your choice location in the United States to see the impact. But NASA has calculated that Antarctica contains about 58 meters of sea level rise. And again, I just want to say, I'm not telling you that's going to be happening in the near future, but certainly that's an end member of a range of situations that's of concern to all of us, whether or not we live near the coast. So feel free to explore that on your own time. It's a great tool to see how sea level rise might affect your local area. Okay, so I'm going to transition to my overall research question, and again, inviting folks to unmute and ask questions if you're interested. But kind of, let's set the stage, saying, okay, well, Antarctica might pose some risks to the global community. And on slide 14, I just proposed the research question: how did Antarctica respond to climate change in the past? What do we know about its ability to change quickly? What is the context for these recent changes that satellites are documenting and field scientists are documenting in the recent decades? And in that picture, you can see one of my undergraduate students. He's standing in a field of glacial debris left behind by a thicker ice sheet in the past. And in the far distance, you can see our snowmobiles. That's our preferred method of travel. So without further ado, let's dive right into the how do we go about answering this question. So, to find out the history of ice sheet change in Antarctica, we have to get there. On slide 15, I show you a picture of one of our camps, obviously far, far removed from wherever we're all joining from today. That's a picture of a camp from a few field seasons ago called Camp Neptune. It was actually occupied by a military-based scientific operation in the 50s, I think also the 60s. So we often revisit places that have established landing strips and that the U.S. Antarctic program feels comfortable dropping us off in. So let's see how we can figure out what the history of ice sheet changes in Antarctica. How do we get down there? And then how do we start collecting observations and samples? So on slide 16, that's my most recent research team, two students from Cal State San Bernardino. We fly to New Zealand. So some of you may have heard of traveling to Antarctica by cruise ship. Those leave from South America, research vessels and commercial travel vessels alike. But for the major U.S. base, the U.S. scientific research base in Antarctica, McMurdo, is accessed from New Zealand by plane. And so first and foremost, we have to fly across the international date line, get to New Zealand. And I'm particularly fond on slide 17 of this image, my screenshot my husband snapped of his flight radar app that shows our plane leaving New Zealand and heading south to Antarctica. Those planes are operated by either the Royal New Zealand Air Force, sometimes the New York Air National Guard. They are, depending on the time of year, they are wheeled aircraft that are able to land on an ice runway. And you can see another member of my research team and my student in the lower right corner on slide 18 in the plane getting ready to head south.
So Claire, I need to tell this story. I think it was the last time you went to Antarctica. George and Carol and I were all watching that plane heading on that, the website that shows you every plane in the air in the entire world, right? And they're all going back and forth across the continents. And down there below New Zealand, there's one airplane flying straight south, and then it went off the screen. And that was
It is pretty wild. I should say that, each season, many scientists fly down there. And so I don't, it's not, It's not a, it's, for the U.S. Antarctic program and the New Zealand Air Force, these are journeys they make regularly for the scientific field season. So nevertheless, certainly for us and for my students, it's a special time every time it happens. So I really enjoy the flight from New Zealand to Antarctica because it shows you sort of what happens as you increase in southern latitudes. So on slide 19, I'm showing you a series of pictures of views out the window. So on the far left, we see open ocean, maybe some icebergs, very small icebergs, but we see open ocean out the plane window. And as we continue our journey, that ocean starts to be covered by sea ice. I am not a sea ice scientist, but I cannot emphasize enough the critical importance of sea ice in the oceanographic and atmospheric and combined climate system. When you look at the picture of the ocean, you see that it's dark, and the ocean is actually very effective at absorbing solar radiation. Once that ocean is covered by bright white reflective sea ice, incoming solar radiation is reflected. High albedo is the word, high reflectivity. So a lot of the solar radiation is reflected back out through the atmosphere into space. And so that's a critical part of sort of the Arctic climate and the Antarctic climate is the role of sea ice in reflecting solar radiation, keeping the ocean from warming. And it's a rabbit hole I won't go down today, but certainly very interesting to explore changes that are happening in the Arctic to sea ice coverage, both permanent and seasonal. So at some point, as we're flying down, we see sea ice out the window, and then eventually we see the Antarctic continent, which is spectacular. There's no other word for it. White surfaces as far as the eye can see, punctuated by rough textures of mountains poking up through the ice. And so it is a remarkable sight. When the plane finally lands, depending on the type of plane you fly down on, it could be 5 or 6 or 8 or 9 hours to get down there. And then the plane lands on the ice runway. And I've shown you a picture of that, pretty close to post landing, my student with his arms outstretched in excitement, having finally made it to the continent. So, all right. On slide 20, I have a picture I took from a mountain that overlooks McMurdo Station. Again, McMurdo Station is operated by the U.S. Antarctic Program, which is operated by the National Science Foundation. And you can see the NSF logo on the top of that uh, fuel tank. And McMurdo is like a small town. Peak population during the scientific season. I've been there when there's over 1,000 people living there. Generally speaking, the staff to scientific ratio is thought to be, I've certainly have heard it is, 1 to 4, so 4 staff members supporting for every scientist. And it is quite the operation. It's 24-hour work clock. There are people who help manage the aircrafts. There are people who manage the galley. There's a scientific research lab. There's a carpenter shop. There are places you can grab a beer. It's its own little town humming with people in support of scientific research, and it's a magical place filled with people who are really dedicated to supporting Antarctic science. I can't say enough about the support staff there, and you're basically looking at. McMurdo Station. It's on a location called Ross Island, and the site shows sort of the mountainous volcanic terrain. And then off to the left, you see basically what's called McMurdo Sound. And McMurdo Sound, for most of the time that I am there, which is typically 2 months for each field season, leaving around Thanksgiving, coming back mid to late January. When we arrive in late November, the McMurdo Sound is frozen over with sea ice. When we are coming back from our field sites in Antarctica, the sea ice has started to break up. You see more wildlife, and eventually you see the U.S. icebreaker, the U.S. Coast Guard icebreaker, coming through the sea ice, making way for a supply ship, an oil tanker, and all kinds of things required to keep this place running. So there is you see the change over even the brief scientific research season. Um, I'll pause just for a moment in case anyone's feeling shy and who wants to ask the question. Okay. All right. So moving on to slide 21, my students, again, you can see in the back of the area a closer view of that sea ice. And we're actually looking at the pipes of the wastewater treatment plant. So if you think about it, it's a town that needs all of the facilities and staff that a normal town would need. But you're looking at out across McMurdo Sound. Um, all right, on slide 22 just gives you a little bit of a flavor of what we do in McMurdo Station. We have to do a what we call a shakedown trip, basically a practice camping trip. That's what you're looking at in the upper left. We meet with the comms team to make sure that we have a schedule for communications with the field station once we get out to our field site. We practice crevasse rescue techniques, roping up and making sure that if someone on a glacier travel rope falls in, the rest of us can arrest ourselves, can stop ourselves from falling, and pull people out of the crevasse. And we of course have to pack a lot of food, burn a lot of calories down there while you're living outside for a few weeks, and so there's a lot of food required to sustain the field team. So McMurdo Station, ideally, we spend a couple weeks there getting ready. Sometimes it's a lot longer if there are flight delays. It's again, really, our work is only possible because of the great staff in McMurdo. Slide 23, we're finally ready to head out to our field camp. Again, if you remember from a few slides back, little yellow stars on the continent. Depending on how far you're going, determines what the plane is. So in the upper left on slide 23, you see a LC-130. It's got skis on it, operated by the New York Air National Guard. And that typically for longer flights, they will put us into our field site in a C-130. Lower right, you're looking at the equivalent of a DC-3, retrofitted DC-3. I think I have that plane number right. My husband would know for sure. And it's a retrofit. We refer to it as the Basler. It's a tail dragger, and you could see the guy fueling up the tanks in the wings in the sort of distance there, and my field team getting ready to board the plane. So travel time to field sites, we often have to stop for fuel, anywhere from a few hours to several hours. Slide 24, to sort of comment on the length of the flight. I like this slide because it shows all of the enthusiasm of my field team on the left. They're cheering and having fun as I take a selfie. And shortly thereafter, they're all asleep, and I am still awake, nervously awaiting the put in. So getting ready to go out into the field is exhausting. And so it's usually a huge relief when we're finally on a plane and ready to go. So it is a lot of work. And in the lower left, I've just given you an example of one of the flights that we took. This was my most recent season, 23-24. And you can see basically a arrow and a star showing kind of where this particular flight took us. Slide 25 shows what a field camp arrival is like. You see,
Sorry, question.
yes,
How far was your destination from the McMurdo,
it
Mac,
really
whatever
varies.
it was
So
called?
yeah, it really varies. So anywhere from 100 to a few hundred kilometers. It's sometimes we go all the way across the continent, and sometimes we go just maybe a couple hour flight away, and so
Okay.
anywhere from 100 to a few hundred kilometers. It
So
always, yeah. Go ahead.
no. Oh, I was just gonna say for me to kind of figure out what distances are like. The one that you have indicated on this slide, what is that distance?
That distance, I'm going to cheat a little bit and just look it up off the top of my head. I don't know, but it won't take me long to pull up that number for you.
Well, I think that was
Just
probably the closest you ever had a field station
yes,
to
that's
McMurdo.
correct. That's exactly right. Yeah. So let me just see if I can't pull that up and get a number for you, an approximate number.
And while she's
Um,
doing that, I'll mention she's also had to sometimes she has been to the South Pole on the way to a field station.
so let's
That's
see.
so cool.
Yeah, I do feel very lucky. So this particular field site was about 700 kilometers away as the crow
Okay.
flies. And then we've been, to the other side of West Antarctica, which is, probably double that, if not more.
So it's big because
Oh yeah.
basically the width of that bay is the length of California.
Yes, yes, that's
give or
right.
take. Yeah.
Yeah, that's a helpful analogy. I appreciate that. Yeah, that's
Yeah.
exactly right. So good question. And
Thank you.
yeah, no, thank you. Yeah, I appreciate the question very much. Yeah. So, so when we first arrive, I'll tell you it's cold. We've been in a station that has heated buildings and everything, but it's cold, but the weather is good if they flew. So if they flew us in, it means we at least have a little bit of clear weather to get our camp set up safely and be prepared in the event there is some kind of storm. Um, and so you can see in the picture on slide 25, we have snowmobiles that have been flown in, oil drums or fuel drums that'll basically fuel our snowmobiles. Sometimes that we also are sent out to the field with aviation fuel drums. You can see on the left-hand side, the yellow tent. That's our kitchen tent, our cook tent. It's the place where we would all gather for team meetings and meals. And then, of course, all of our supplies, boxes and boxes of our supplies, thousands of pounds of gear, and it often takes multiple flights. So you really do need a few different good weather windows to make this happen. Okay, so let's see. On slide 26, you can see another form of um, field drop off. This is from a C-130. They basically do what's called a combat offload, where they just open the back of the plane and we walk out of the back of the plane. And on previous flights, they will have basically dropped off all of our cargo pallets, which you can see on slide 27. It's my colleague walking out to where cargo has been dropped in advance of our arrival. And this picture actually gives you a great idea of what we're walking into. We are geologists, so we're interested in visiting where rock is exposed. And so here you can see there's mountains in the distance, but a lot of what you're looking at is just flat white all around. And this is a moment of excitement for us, anxiety, getting everything set up, making sure everyone's feeling comfortable, has all the gear they need, and ready to get camp set up and get to work. So we're left behind. And you can have slide 28. I just show you a picture of the C-130 leaving us. And at that point, we're on our own. The longest field season I've ever done is over 40 days. Some are shorter. But at that point, you really need to be self-sufficient. So that's a reason for all of the preparation, all of the training, is that you become your own sort of self-sufficient research-based station without running water or heat or medical facilities or anything like that. So it's an exciting moment, and also a moment where a lot of things that you've been preparing for come to fruition. So part of our base camp, we have to set up tents. You'll notice on slide 29, the edges of this tent are buried in snow. There's a lot of guy lines for security, a lot of stakes into the ground. We need to be prepared for high winds. I've heard stories of scientists in camp where the winds were strong enough to roll snowmobiles, which are several hundred pounds. And so really, even though we're there on a blue sky day because the planes flew, we're really focused on making sure we get everything set up so that when weather does go bad, which it always does, we're ready for it and we're able to stay safe. And the most recent field camps shown on slide 30, that's a pretty good picture of what it's like. Those are the tents that we sleep in. And it's quiet and cold, but also beautiful, and really special to have the ability to sort of set this up and get to work. So, okay. When we get to work, we are primarily, as I mentioned earlier, traveling by snowmobiles. And so you can see that we set up basically a gas station, and we pump, our snowmobiles full of fuel. You can see a lot of red flags. Depending on the camp location, we often basically flag safe routes. In the event that weather changes quickly and visibility declines because of blowing snow, you really need the ability to effectively travel with no more than a few meters of visibility in front of you. And so if we're going to be in a camp for a long period of time, or we're particularly concerned about that risk, we will plot out a lot of flags along safe routes so that you have a way to get home even if visibility is severely compromised. And visibility is not just for windblown snow in the air, but on a very cloudy day, you lose shadows in the snow surface. And so that limits our ability to avoid crevasses or particularly steep slopes up or down if there's no what we call definition. So cloudy, very overcast days, even without a big storm, seriously compromises our ability to travel safely simply because there's no shadows that help our eyes tell where it's safe to drive a snowmobile. So we rely on a flagged system as well. Okay. Slide 32, it's a picture of a student. We often have to move camp in the middle of seasons. And so that is a picture of one of my students in the middle of a camp move, where we're moving basically from one part of a mountain range to another. And we've packed sort of all of our belongings on the back there. Okay, so that's sort of the travel log. I'll pause for a second in case anyone has anything to add before I start to get into some of the geology.
Maybe very quickly, you can tell us about the manner you put the flags and how you know that this is safe. Like, is this like based on history, like people had accidents in that spot before, or what is the story?
So really good question. Thank you. So some places we have been previously occupied. But most of the routes that we travel have not, and certainly not in recent memory. And so the only way that we know, I should not say the only, two ways that we know it would be safe to drive a snowmobile is first of all, simply by being on the snowmobile and looking out ahead, and if we can look for basically changes in the surface of the ice, depressions, inconsistencies that suggest there's a big crack. We also know how glaciers flow. So steep slopes, any kind of drop off, even if you can't see them, will have what are called extensional crevasses, where the ice is basically stretching past its breaking point and opens up big kind of broad crevasses, and those are typically so big that they would see even under thick snow. You would see those. So the first and foremost, we are simply navigating by eyesight and by our knowledge of the terrain and of sort of how glaciers flow. If we get uncertain, there's always a mountaineer who's with us, who is sort of in charge of safety as a counterpoint to the scientist in case the scientist is feeling particularly cavalier. It's good to have the safety decision making distinct from the scientific decision making. And the mountaineer can get out and probe with an ice axe or something else ahead of the snowmobiles just to make sure there's not something we're not seeing. But for a snowmobile sized hole, there will be some kind of manifestation on the surface and some indication in the terrain that there's a loss of elevation or something that would create a crevasse. The other thing that we've been able to do recently is use satellite imagery. So you can ask the U.S. Antarctic Program in advance. There's a great organization associated with the U.S. Antarctic Program called the Polar Geospatial Center, and they are able to build very high resolution maps and acquire very high resolution imagery for you in advance of your trip. So we can also navigate using satellite imagery, but I would never do that alone. We are always aware of the possibility of a crevasse, and so we bring with us a kit to do roped snowmobile travel. We have never actually done it because we tend to just avoid areas where that type of precaution would be needed. But in general, we're simply just reading the signs in the snow surface to see if it's safe to travel. So great question. Anything
Thank you.
else? Yeah,
Yeah, one more.
yeah.
What was the longest tenure that you had down there?
The longest on continent, typically we're on continent for about 2 months. That includes time in McMurdo. And the longest field season, just tent-based field season, was over 40 days, about a month. But we've done shorter field camp stays, but the longest was a little bit over a month. So.
Wow, and so you guys got to bring. Well, actually, I mean, it's obvious. You got to bring all the supplies for the entire time, right?
Yes,
How
occasionally,
how how
depending
do
on
you
the
get it there?
location, all
Is
by
there is,
plane.
th- is there some there already waiting, or you have to bring it all?
It's possible that earlier in the season, the program dropped supplies that we had requested for us, but the bulk of it comes out by plane with us or potentially a day or two in advance of us. The bulk of it is traveled. And so some projects are traverse based. where basically everything is dragged. But for our projects, it's put in by plane. And so, yeah, so it all comes with us. It is a lot of stuff, tons of cargo. And that cargo, it actually, it's part, a lot of our planning is allocating that cargo across flights, across good weather days from McMurdo. It's really labor intensive. It's a good team in McMurdo that manages all the flight logistics and the cargo, and it's quite the operation. It's a huge logistical challenge. So yeah, you need everything. You bring everything. Occasionally, in the very, maybe in the 2000s, we had some trips that were supported where we got a resupply, either because someone on our team was flying out earlier, or so you can occasionally get a plane flight with some resupply, but that's not ever guaranteed, of course. And so you bring out everything plus a little bit more that you think you might need. We've been delayed in our camp pullout before by over a week, and so that's why you pack a lot.
I've heard of that. Yeah.
Yeah, so you pack a lot of extra stuff. So okay, thanks for the questions, everyone. Appreciate it.
So you said something that I've been sitting here trying to imagine, that you said it's very cold and it's very quiet. And well, the very cold, of course, but the very quiet I hadn't thought about. And I was thinking that except for the sound of wind, there shouldn't be any other sound because there are no animals, there's no machinery. And then also, if you could first of all describe how that feels, and also how the air feels, because there are no hydrocarbon fumes or any man-made smells. So
Also the
how does
penguins.
what?
The penguins. I want to know about the
Well, the
penguins.
penguins are not there where they are. They're at the coast. So
Oh man, yeah. At some point, we need to get to the penguins.
so how does that feel to be somewhere that there's like no noise? Do you freak out? Do you if you could just talk about the sensation of that, I'd be grateful.
Oh, happy to.
Can I add, because I've been waiting till you finish, but since Sam asked, I want to add a small sentence to his question so you can answer everything together.
Yes.
Does it take a certain psychological strength and temperament to do this work? Because as Sam mentioned, it must be very stressful. Is there some kind of psychological training that people do, or is there a certain psychological screening? Because not everybody can take loneliness on that level.
These are really wonderful questions. They're insightful. First, I will say, Sam, you brought up wind. And the wind is actually, I think, one of the biggest challenges. I have had seasons where the wind was relentless, and every morning I would wake up and hope that I would hear quiet, and instead I would just hear the deafening sound of winds. So I've had some projects in valleys where the katabatic winds, these are gravity driven winds, very cold air from the South Pole basically gets pulled by gravity down these glacial valleys, and so if you're working one of the glacial valleys, you are just living in a wind tunnel for a month. And that noise is so it's related to the psychological question. That noise can wear on people. So you were right to bring up wind as the exception, because wind is a huge challenge, not only from an audio perspective, but it also means you can set nothing down. You can never, you can never set your gloves down. You can, you also have, you're constantly sort of worried about the integrity of any either, equipment or your tents. And it's also takes the cold factor and amplifies it dramatically. You're already working to eat enough calories to maintain your body temperature, and when the wind is constantly transferring your heat away from from you, it's a huge challenge. So windy days are the days that I worry the most about the team, and kind of everyone's ability to sort of keep it together. Wind presents a challenge, for a frostbite challenge, especially if you're driving on a snowmobile for a long distance into the wind. You really have to make sure that every single square centimeter of skin is covered. So wind is a huge problem. But let's get back to the quiet part. It's I find it reassuring, comforting. It's if you seek out silence and you you occupy it in silence, it's a wonderful thing. As soon as you move, of course, you're always walking on snow until you're at a you make it to the mountains. Our camps are always on snow, and so as soon as you're walking on snow, then that's a sound, the sound of your own footsteps as the snow kind of crunches beneath you. Wind in tent material, even a light wind in tent material might make a sound, but otherwise it's very um I find it comforting, actually. And honestly, I think a big part of what the privilege of being an Antarctic researcher, it certainly does for me, is it gives you perspective. It really makes you realize how big the world is and how inconsequential we are. And the silence has a way of feeling vast. We've often joked that one of the scariest things that could happen is if we were all in the tent, which happens often, and we heard someone approaching. Because how could they have gotten there? So your world is pretty
The
well defined.
Antarctica Blair Witch Project.
Yeah, pretty
That's
much. And of course, and again, as John mentioned, the sun never sets while we're there, and so you become oriented to the sun rotating in the sky. Your eyes learn what the shadows look like on a clear day at 4 p.m. versus at 9 a.m. Your eyes get adjusted to that. There are some parts of the day that are colder than others, depending on where you are on the continent and the sun angle, and so you do attune to the time. Every time zone is in Antarctica, and we basically pick our clock. So the station requires that we have to call in every every day. We have to report, and if we don't, eventually they will mobilize a search and rescue party. So there's a daily check-in, and so we always just decide that we will stay on the same time as McMurdo Station, even though we could be in we're in a different we could be in a different time zone. So we just decide whatever 7 a.m. is in McMurdo Station, which follows New Zealand time, then that will also be our 7 a.m., even though we've had field sites in other locations that are in different time zones.
Claire, would you mind if I ask the science question? I know you've got a lot of questions, but I don't think you've got one question about the science.
And let
Um,
me, Benjamin, I
Does
appreciate you
it
saying that
does it
too.
include
Let
data?
me let me suggest that you ask the question, but I think just in general, if we could, because I know that Claire really hasn't gotten to the science yet, and I don't want her to be here all day. So ask your question, Benjamin, and then maybe for everybody, as much as Claire would be happy to answer little questions. I think
oh
if
yeah,
if if there are
I'll do.
questions about
I'll
Antarctica.
say I'll say what John is not saying. Claire, it's really great of you to come in here and talk about your feelings. And I know you've had a lot of questions about your feelings. This is a science room. Um, hopefully, we can get to the science. My question was really, really effing specific. What data are you collecting and how?
Yeah,
Yeah,
absolutely.
let her get to that. She's
Yeah.
that's coming. Yeah.
Yeah. I'll get to that. And just someone did ask about the psychological part, which I know is feelings. We don't
I
go
knew
undergo
data
a
was coming.
Yeah, data are coming. Yeah. We don't undergo a specific psychological examination. And so that's not required. If you are going to winter over on the continent, I believe there's a more scrutiny about psychological examinations. And I will just say, and perhaps the clubhouse members know this, the most difficult psychological thing is dealing with your teammates. That is the most difficult thing. You need to get along with people for the whole field season and maintain, stay a functional research unit. And so that's a life lesson for you. It may be really cold and physical conditions may be challenging, but it's really the interpersonal that is the hardest psychological part. Okay, so yeah, back to the science. So what are we doing? I mean, the first thing that we're doing is we're climbing around mountains. And so on slide 33, I've shown you a picture that gives evidence of ice sheet occupation in the past. You're looking at a very polished rock with scratch marks on it. The scratch marks are in different orientations, and we can tell how ice sheet flow direction has changed. from which you can infer a past topography. You see the smoothing, of course, which is, glaciers contain a lot of rocks, particularly at their base. And so a thicker ice sheet flows over a larger expanse of rock and polishes the rock beneath it as it flows over time. And you also see rocks that are perched. So in this particular location, there are no humans going around building cairns. You see, in fact, actually that the glacier has lowered rocks onto other rocks as it thins, and so those are some of the indications that we are looking for, that the ice sheet was larger in the past, and we'll talk about how we can actually date these deposits going forward. So lots of evidence of a thicker ice sheet. Slide 34. You can see sort of a bathtub ring of gray, less weathered rocks on the lower part of the image, and red, more oxidized rocks on the upper part of the image. And we see these bathtub rings throughout Antarctica, showing basically evidence of a much thicker ice sheet, and evidence that the ice sheet occupied that higher elevation for a period of time, long enough to leave a bunch of rocks there. So another indicator we look for is a rock that looks like it doesn't belong. So on slide 35, we see a a light colored granodiorite, perhaps, on top of a much darker metamorphosed rock. And so that was not from the mountain it's resting on. It has flowed to that location in glacier ice when the ice sheet was much thicker. So we see evidence of all of these past glacial deposits of an ice sheet that used to be much bigger and then melted, thinned, retreated to its present thinner, smaller state. And there's a lot of linear features of rock deposits indicating a past ice margin. So if you go to a glacier today, you'll see at the margins of the glacier lots of rock. These glaciers are constantly eroding the bedrock surface beneath and transporting those rocks as ice flows to its margins. And Antarctica is no different. So when we go to exposed rock, we expect to see these locations of a past ice sheet margin. So slide 37, you see a colleague of mine standing on what we call a glacial moraine. It's a linear ridge of glacial debris, again, that marks a past glacial high stand. Um, some of these deposits are very old and perched hundreds of meters above the current ice surface. So on slide 38, you see basically a rock garden, if you will, of giant boulders that could not have fallen or otherwise been deposited except by a much larger ice sheet. So how does this work, right? We've already talked about basically the glacier ice is going to flow down flow across bedrock, and it entrains rock by a few different mechanisms, by abrading, by quarrying. And then the ongoing ice flow transports large quantities of rock down ice stream, if you will. In the same way, we talked in the beginning about the ice sheet flowing from its center to its margins. And so all of that ice is carrying rocks. And as the ice gets thinner, it leaves behind its cargo. So we want to find out how, and then we know how, we want to find out when these were left behind. So what we do is we are collecting samples of these rocks that we know are evidence of past ice positions. And this is not, slide 41 now, this is not a new idea. A famous geologist, at least in glaciological circles, John Mercer, shown in the lower right-hand corner, in the 60s, visited a field site that we reoccupied in the 2000s, and mapped all of the types of things that I'm telling you about, and said, quite insightfully, we have to await absolute dating. So if we were all hiking around the mountains of Antarctica, you would see the evidence everywhere. Giant rocks, piles of rocks, lines of rocks perched well above the ice surface. Goal, of course, is to date those rocks. And in this image in slide 41, I'm showing you an abandoned camp from Mercer's work in the mid 60s. There was different times. The US Navy was dropping scientists off with big helicopters. They did not have the environmental sort of precautions that they have now. And so you can still find vestiges of past research trips around the continent. Okay, so slide 42. This is a bite of physics. Here's your bite. Can we date glacial deposits? Yes, we can. We rely on cosmic rays, not really cosmic nor rays. They are high energy particles generated in things like supernovae that arrive at the top of the Earth's atmosphere and interact with atoms in the Earth's atmosphere, generating a cascade of what are called secondary cosmic rays. So we're being struck by them right now. If you're a pilot, you are struck by more of them, more of their energy because you spend more time higher up in the atmosphere as the cascade of reactions of collisions makes its way down through the atmosphere that loses some energy. Nevertheless, the secondary cosmic ray flux is still energetic enough when it reaches the Earth's surface to penetrate through the rock surface and interact with molecules in the actual crystal lattice. And so, for example, for quartz, silica, and oxygen, when a highly energetic particle interacts with an oxygen atom, it breaks that atom apart, changes its nucleic makeup, turns it into a new atom. So quartz is one of the most common target minerals in cosmogenic nuclide analysis. And it's because it's abundant and because when highly energetic particles interact with that oxygen atom, it can produce carbon 14, also produces beryllium 10, which is a very common cosmetic nuclide used in geochronology. So let's pull out our trusty periodic table, which, you know, what a magical thing, the periodic table. For our purposes, let's focus on the top part of it. If you look at the oxygen atom, right, eight protons, when it's struck by a highly energetic particle and becomes beryllium 10, you can see it has to lose 4 protons and a couple of neutrons to become the beryllium 10 isotope. One of our most recent studies used carbon 14. So again, you loses fewer subatomic particles, but those collisions with the secondary cosmic ray flux and quartz atoms can produce some very helpful chronometers for us, because the longer a rock is exposed at the surface, the more of these nuclides accumulate, and that production is well known. The production of a cosmetic nuclides in a mineral lattice is a function of latitude. The Earth's magnetic field deflects more of the cosmic ray flux at lower latitudes than at higher. It's a function of altitude. A rock higher up in the atmosphere receives a more energetic cosmic ray flux than a rock at lower in the atmosphere. So there's the production rates are a known quantity, studied and calculated and sometimes refined by the scientific community. But once we have a rock and we're able to isolate the cosmogenic nuclide that we are interested in, the amount of that cosmogenic nuclide is a function of how long that rock has been exposed. And that is how we are able to use rocks as effectively clocks. As soon as the ice leaves a location, the production of cosmogenic nuclides begins. And what that means is we can then go around and use mountains as dipsticks. So we're I take you through it on slide 44. That's yours truly, many years ago, at an ice margin, collecting a rock that ended up with an exposure age. I think that one had an exposure age of maybe 1,000 years. But basically, the ice thins and exposes new rock, and that rock is exposed to cosmic rays, begins to accumulate rare nuclides. And this is the key point. The nuclide shouldn't exist in the nuclide can't already exist in the mineral, or if it does, you need to know the quantity. So the rare part is key, right? It's one that has not yet been produced in that nuclide. So you have basically the ability to start at 0. And then to actually isolate that nuclide and measure it requires laboratory chemistry. We have to get from a giant rock to atoms. And so that starts with crushing, sieving. We have to separate mineral grains using heavy liquids we can adjust the density to separate, let's say, a quartz grain from a feldspar grain. We have to make sure the quartz is pure So we often soak that quartz in hydrofluoric acid, or what's called etching, to get it so that there's no other source of the nuclide that we're interested in. There's nothing else that will interfere with the analyses. We ultimately react, we create basically a beryllium oxide. This is months and months of lab work. And then that pellet goes to an accelerated mass spectrometer, where it is, the number of beryllium tin atoms is measured. It's a ratio. The beryllium tin is measured ratio to beryllium 9. We spike our samples with a known amount of beryllium 9 to have the ability to measure the ratio of beryllium tin to beryllium 9. I briefly saw a comment about radiometric. Yes, these are radioactive isotopes, which of course we have to account for in the production rate calculation. So beryllium tin has a half-life of about 1.4 million years. That is that's a nice long half-life, such that even if just a small amount of cosmogenic beryllium tin is produced, if just a small amount is produced, then we still will be able to measure that small amount years later, because the half-life is so long. There'll still be enough present in the sample. I'm now fully into the bite here, so if someone has a question, please feel free.
Uh,
Claire, I have a quick question. The since beryllium 10 has such a long half-life, how do you know that it wasn't there from before?
Ah, wow. Great question. Such a problem. It has a name. We call it inheritance. It's a good thing for humans, bad thing for cosmetic nuclide dating. Um, basically, what happens then if a rock has been previously exposed is it is so distinct from the rocks that have no inheritance. So we do collect rocks that when we're in the field, we think, oh, this has definitely, newly exposed. It hasn't been around the block in Antarctica. It hasn't been exposed multiple times. But we do encounter rocks that have inheritance, and those are quantitatively distinct from the population that had no inheritance. There's another isotope that we measure, carbon 14, which has a shorter half-life, less than 6,000 years, 5,730. And so that is, we can tackle the inheritance issue that way, as well. So
Kind
great
of
question.
compare basically the two results, I guess, and
Yes,
see.
exactly.
Yeah, right.
Exactly. And we're also often measuring multiple nuclides. So um, aluminum 26 is another cosmogenic nuclide, and it has a half-life about half of beryllium 10's half-life. And so we also collect samples of bedrock. And we're able to, even though we know the bedrock has been um, covered and exposed many times, that if we measure two nuclides with different half-lives, we're able to determine, okay, it could only have been exposed for this long of a period of time. We can basically constrain a much more complex exposure history, how much burial versus how much exposure. So while you can't say it was definitely exposed from 40,000 years ago to 30,000 years ago, you can say in total, these two analyses limit the total amount of time they could have been exposed. So it can get more complicated in terms of whether you're measuring it in bedrock, which we know will have inheritance, or a glacial erratic, which are ideally we would like a rock that has been freshly quarried from the bottom of the ice sheet, kilometers below the surface, and left behind. So that when we pick it up, it only has the most recent exposure history. But of course, as you're pointing out, that doesn't always happen, particularly with if we're choosing an isotope with a long half-life. Okay,
Claire,
I've made it. Oh, yes,
on,
go ahead.
on
Yes.
that same point, very quickly.
Mhm.
Do we know that since we discovered what we call the ozone hole, or that thinness of the ozone layer above the Antarctic, has this messed up this dating process? Because now there's less ozone, so now probably more cosmic rays are penetrating the atmosphere, and so it's accelerating that transformation inside the rock, sort of. Or am I off because this is like 50 years and it's too small?
It pretty much to the scale is wrong, as you're suggesting, that it's the effect, and the time frame, the marginal effect on the time frame is not enough to to impact the analyses that we're making. So that's not on the scale of sort of thousands of years of accumulation. It's not enough to see an impact of atmospheric changes in atmospheric composition, which would have a small effect on the cosmic ray flux, and then ultimately a smaller effect over thousands of years on our analyses.
Great, thank you. And we have a question from chat from Elliot. He asks,
Yes.
these cosmic rays, are they sort of constant over time? Like, is it the same frequency, or do they hit rocks and ice at a certain rate that is knowable already, or how is it going on?
This is a great question. So for our purposes, the cosmic ray flux is effectively constant, but it is not constant on shorter time frames. So, for example, there's a solar cycle that affects that causes fluctuations in the cosmic ray flux, but those fluctuations are on the order of decadal. Anyway, a much shorter time frame than we are looking at, and so the overall cosmic ray flux, when you look at it over thousands of years, those short-term fluctuations are sort of part of kind of gets lost in our calculation of the cosmic ray flux. So it does fluctuate, but not to such a degree that it affects the accumulation of isotopes in rocks when we're looking at millennial scale change. And there's some physicists on this call that I'm sure would love to chat more about the cosmic ray flux. Yeah, so John's also, I think, weighing in, but it's a good question. So,
Great.
um,
Thank you very much.
oh yeah, no, thanks you guys. So we have slide 45. I'm going to just show you some bad art to illustrate kind of how we use mountains as effectively dipsticks or time indicators. So I have a picture, slide 45. I have a student walking down a rocky hill slope toward a glacier. You can see people in the distance to give you an idea of scale. And then you can see all kinds of glacial erratics on this hill slope. And so this is a classic example of what we look for. Like when we propose the science, we say, look, we know there will be glacial erratics here. We know they're going to be a rock type that we can use. And so let's please allow us to travel to these mountains to sort of track long-term ice sheet retreat. And so with apologies for this terrible computer art that I'm showing you on 46, I've just basically made you a simple sort of cartoon. I noticed someone asked if we, take acid or lab materials into the field. We do not. These are our rocks get put on a boat. We don't see them until longer, we don't see the rocks that we collected until April or May the following year. So it takes a while for us to get them back. And so all the lab analyses happens stateside. But let's just, for the moment, imagine that we had a sensor in the field and we could point it at a rock and estimate basically how many years worth of cosmic nuclides we have. We cannot do this. Again, we have to take the rock home. But let's say we could. Let's say we say, okay, great. This upper rock on this hill slope has 15,000 years worth of cosmogenic nuclides. Then in my silly little cartoon, what have we learned? We know that the ice sheet retreated from about that location 15,000 years ago, that it was covered by ice. On the order of about a meter of ice can attenuate the cosmic ray flux, effectively blocking rock from accumulating cosmic nuclides. Once the ice sheet leaves that location, as I've mentioned before, the rock starts to accumulate those nuclides in the mineral lattice. And so as we work our way down the mountain, we can develop a time series. And back to John's question about inheritance or long half-lives, meaning that there's isotopes left over. The other thing that helps us identify samples with inheritance is if there's a strong deviation from this time series. But generally speaking, as you climb up a mountain, you have more exposed rock at the top, less exposed rock at the bottom. And so in this way, sort of traveling around the mountains can provide, basically, there's just records along the hillsides of where the ice sheet used to be. So I'm going to give you just a couple of examples from recent studies. I'm almost done here. So it's slide 50. You can see an image of a mountain rising above a glacier. In this situation, actually, we were quite close to the coast. And there were actually bird colonies near us, no penguins, but bird colonies. But so the ice surface about 20 meters above sea level, and our highest sample was about 175 meters above sea level. And our ages told us that that highest sample had a surface exposure age of about 20,000 years. And so that tells us, okay, the ice was thinning at about a centimeter per year, that the ice was lowering itself about a centimeter, or basically losing mass and lowering down the mountainside about 1 centimeter per year. And another example from the same field season, pretty close to sea level, ice surface 75 meters above sea level, our highest sample at the top of a mountain overlooking the glacier, about 300 meters above sea level. Ice was at least 225 meters thicker, thinning rate again of about a centimeters per year over 17,000 years. So we're getting the rate of ice retreat, we're getting a maximum ice elevation, or potentially if it overrode the entire mountain, a minimum maximum ice elevation, and a rough timeline. Well, when was the ice bigger? And so here's an example study on slide 52. I don't expect you to read that abstract, but this is just an example of a study that used cosmogenic carbon-14 in samples near the locations I've been showing you pictures of, in a place called Northern Victoria Land. And so this study showed that basically the ice had finished thinning by around 7,500 years ago, so that most of the ice retreat was complete about 7,500 years ago, effectively separating it, if you will, that long-term change from more recent changes. So this is just an example graph from that same study. On slide 53, we plot our samples relative to elevation on the y-axis. You can see here. On the x-axis, the lower x-axis, you can see the concentration of carbon-14 atoms in a sample, atoms per gram of sample. The colors represent different field sites, and those dashed lines are showing you ages associated with those C14 atoms. And it's typically this age elevation trend shows us higher elevations, older exposure ages, to lower elevations, younger exposure ages. So this is a nicer version of my little cartoon I made you of the mountain. So finally, what's the history of Antarctic ice sheet change? My overly busy slide 54 is a lot going on here. Most surface exposure age studies from Antarctica show millennial scale thinning rates of 1 to 5 centimeters per year over thousands and thousands of years. Today, satellites, field measurements are showing meters per year in some places, particularly Thwaites Glacier, the glacier I mentioned in the beginning. So we're seeing 2 orders of magnitude increase, acceleration in ice sheet thinning. And in this way, I think of our work as basically providing context, this long-term context for these short-term changes. So what's next?
Can I ask you a question about slide 53 before we go on?
Of course. Oh yeah, absolutely. Yes.
So slide 53 is the is the science. It's
Yes.
got the data.
Yeah.
Um, is this data available? Is the data that this is based on available? Where do I download that?
You can go to a site called ICE-D, ICE-D. It is a database.
ICE-D.com.
ICE-D, ICE-D. I believe it's .org. But if you Google ICE-D,
Yeah.
you'll see all exposure age data from all over the continent.
Right. Now, we talked about the problem with inheritance. Is this data filtered for the inheritance problem, or is this the
Yeah, these
unfiltered
are
data?
not, so this is not, none of these samples have inheritance in them. If they did, you would have seen, they would be way off the axis. They would have much higher carbon-14 data. Sorry, much higher carbon-14 concentrations. They would be way off the axis.
Right. Well, I was just wondering if the data that's at ICE-D is the filtered data or the unfiltered data.
Unfiltered. You'll see it all.
Right.
All
Do
of
you
it, all
do you
the
think it's
isotopes that were
important
measured.
to publish the unfiltered data?
Some studies do. So you'll see that you can look like some studies, and this
Oh, that's not what I
paper.
asked. That's not what I asked.
Oh, okay. Yeah, sure. Yes.
Do
Everyone should
you
know about the
think
inheritance.
it's important to publish the unfiltered data?
Yes, that's right. No one,
There we go.
everyone
There we
should
go.
know the
John,
whole data
there's your
set.
girl right there. There's your girl.
And
Done and
I
done
was
and
sitting here.
dusted.
Objection, Your Honor. Leading
Done and
I'm
question.
so
dusted.
Claire.
Objection, Your Honor.
You've
The
handled
question was
Benjamin
leading.
as well as anybody has ever handled Benjamin.
Fair questions. Fair questions.
Done and dusted. I know it's a fair question. Look. Sometime, Claire, I'm going to sit you and John down. You can talk about this, and we'll get you patched up. You can get through this. It's not a permanent schism in your relationship, which I can help. But it's going to be a hard time because John takes the other view, and this is an important view. So anyway, let's continue. We'll do the We'll do the family therapy later. Thanks, Claire. You're wonderful.
Well, I'm pretty much done. Just saying one of the things that we can do, that we're hoping to do in the future, it'll be a while, is to, instead of just collecting rock above the surface of the ice sheet, to drill through the ice and collect rock beneath the ice sheet, to determine if that that rock has ever been exposed to the cosmic ray flux. And there's reason behind doing this. We There are multiple ice sheet models that are they're developed around, from different institutions around the world, that calculate that the last time atmospheric CO2 concentrations were as high as they are today, it's about 3 million years ago, that East Antarctica, huge parts of East Antarctica, big marine basins in East Antarctica, deglaciated. And that would be a significant outcome for civilization, coastal communities around the globe. And so we hope to go to these locations where models have predicted that East Antarctica could have deglaciated, when CO2 levels were last this as high as they are today, and drill through the ice, collect rocks, and perform the same analyses to see, what, if there's any evidence of exposure to the cosmic ray flux well beneath the ice. And so it'll be a while. This developed proposal's been in the works for a while. Again, it's not just me; lots of colleagues. And Yeah, so that's what hope comes next. But otherwise, that's all I have.
That's great, Claire. I was thinking as you were talking about that, I was thinking about, because I think if you go back 20,000 years, you're talking about toward the end of the last glacial period, right? But it's still pretty
Yes.
much full roaring, I think, at 20,000 years. Is that right?
It really depends on where you are on the globe. It depends on where you are in Antarctica. So the ice age, generally speaking, yes, we think of sort of a global ice age occurring, in the United States, maybe between 20 and 30,000 years ago. There are locations in Antarctica where we've measured the last glacial maximum as recently as 17,000 years ago. So there's a lot of global variability in how what the rock record is telling us about maximum ice position. So when I think about an
Mm,
ice age, I'm thinking about ice extent.
yeah.
Other people are thinking about ice age from like a climatic or potentially an oceanographic perspective. The last glacial maximum, which is what we call the most recent ice age, manifests itself in different ways around the globe. And so, yes, roughly 20,000 years, depending on where
Well,
you
here's the
are. Yeah, go
yeah,
ahead.
so here's the reason I was asking. I think so. Your numbers for kind of when the how high the ice was at that time maybe
Mhm.
gives you a sense of kind of how much you can integrate over the topology of Antarctica, figure out kind of how much water that is,
Yes.
and that plus the other water that's locked up in the Arctic regions, the total of that has to be something like enough to take sea levels down by what, 100 meters or something, I think, or is
Yes,
it
that's right.
300 meters?
No, I think in the last ice age we're looking at sea levels lower. gosh, 120 meters. It's not a,
That's what I thought. Yeah, I
yeah.
think that's right. So broad strokes, take the oceans down 100 meters. You gotta say, where did that ice come from? Have people? I assume people have kind of done that and said, oh, okay, we can kind of see 30% of that in the Antarctic, or if you just integrate over all those valleys, how much water that is. Does it
Yes.
all kind of suss out?
This is it's a great question, actually somewhat controversial, because there are meltwater pulses that are identified in, for example, coral records or other coastal deposits. So relatively quick increase in sea level that's documented in the geologic record. And some scientists like to say, oh, it must have come from Antarctica. There must have been a big release of water from Antarctica. And on the terrestrial sort of the geology side, people say, at that time frame, we don't have a big release of ice from Antarctica. So are people doing that work? Yes. People reconstructing last glacial maximum ice in Antarctica, tracking when that ice was released. And there's always a healthy conversation between people who see specific pulses of sea level rise in the geologic record and sort of oceanic and coastal environments, trying to match it with what we see on the continental side. And yeah, there's always a lot of good scientific discussion about that. But generally speaking, yes, can we put ice back, if you will? We can certainly on the whole of it. Yes, we know how much ice, although I will tell you I don't know exactly off the top of my head right now, but we know how much the volume of ice basically that has been lost over time by relatively actually simple geometric calculations to basically reconstruct numerically where past ice levels and how much ice that would have been relative to today.
Yeah, I just love those just order of magnitude kinds of calculations, just to see if you're kind of in the ballpark there.
Yeah.
Yeah, anyway, thank you.
Yeah.
Hi, Claire. Thank you for having me up, and wonderful talk, Claire.
Thank you.
I am trying to understand how one might separate biogenic alterations from microbes from the cosmogenic legacy. Not legacy, but what's that word that you use for that?
Inheritance.
Inheritance, yes.
Mhm.
And is it really an issue, or is it not an issue? And finally, I'm actually a former colleague of Jeremy Dotsworth, also from CSUSB.
Oh, wonderful.
So I think we have some history there.
Yes. Oh, that's great. Oh, that's wonderful. Um, yes, Jeremy is still my colleague. I'm happy to hear that you know him. For if I were so Pete, you can do short, like depending on the isotope that you use, you can measure cosmogenically produced nuclides in soil, for example. And that might be a situation where you would have more biogenic, you might have a biogenic or a biological process that affects, for example, how much carbon you are measuring in your sample. For our purposes, we work really hard to ensure that we are just looking at quartz grains and ultimately beryllium atoms from within the crystal lattice. um, and so that all of the HF etching, hydrofluoric acid etching, and lab work isolates it from those any biological processes that would have been occurring, although within the mineral lattice we don't expect there to be biological processes.
Wonderful. Thank you very much, Claire.
Thanks for the question.
Yeah, anybody else?
Yeah, sorry, just quickly, within the ice lattice, you don't expect any biological activity because there's no organism trapped there, or it's too cold for the organisms that are trapped there to do any activity?
Great, very important distinction that you're making. So we are measuring it in the mineral lattice of rocks. You can measure um, uh, cosmic nuclides produced in the ice, and that is another area where I don't, it's not my area of expertise, but they do measure cosmogenically produced isotopes in ice cores. And that there may be some biological influence there. I haven't heard of biological influence in Antarctic ice cores, but that doesn't mean it's not a thing. But when I'm referring to the mineral lattice, you're correct that ice is a mineral, but I'm referring to the lattice actually in the rock samples where we don't expect any biological activity.
Okay, thanks.
Yeah, good question.
I want to apologize because I came right, I guess, at the end of the presentation and for the Q&A. But it seems that you're, I guess, you're a geologist. I'm assuming,
Yes.
or okay, so you work with climate scientists, or you try to address that front by any chance?
Yes. So we are. I would say that our data, and so the ICE-D database, for example, that the information I shared with Benjamin, those data are used by modelers that are looking for past elevations of the ice sheet to include in their ice sheet models, and those ice sheet models rely on sort of interactions with climate models to drive the changes. And so, while I am not a climate scientist myself, our data inform ice sheet modelers who also use climate data to inform how they run their models under certain climatic conditions.
Yeah, I think one of the issues, especially with deforestation, is that the older trees that are still in the ground are much more important for the soil and what's going on like with the landscape in terms of how the biospheric regions are managed, and that just planting new trees doesn't really address the issue because the way the root networks form are not as rich, right? So I think this it's not like we could just plant trees, right? But I don't know if you're familiar with those dynamics.
Not like the carbon cycling, the science around carbon cycling is vast and definitely outside of my area of expertise. So I know there is some good research in that realm, but that's not something I feel confident speaking to. But you're right to acknowledge the complexity of the role of trees in the carbon cycle. There's a neat animated graph I recommend called the carbon dioxide pump handle that shows you rising CO2 in the atmosphere at different latitudes. You can just Google carbon dioxide pump handle and watch the video that shows you the graph through time. The graph animates the graph through time. And just to highlight your point about the importance of trees, in the northern hemisphere where there is more land mass, you see actually a drawdown of CO2 in sort of peak spring months, spring and summer months, when the trees' leaves are pulling CO2 in. So the role of trees is actually huge in carbon cycling and complex. But again, here I am talking about something I don't know as much about.
One of my peeves in terms of carbon emissions is the dynamics of the emissions, right? That we know it's not just carbon, right? There's there's other greenhouse gas emissions, right? Like nitrogen, but it seems carbon is the most prominent. That's why it gets pitched so much. I'm imagining.
So they can measure what's called the radiative forcing of the different greenhouse gases. And so one of the reasons that carbon dioxide is focused on is not only for the measurable changes in the atmosphere, the concentration of that gas over time, but also that gas has an impact on Earth's energy balance. And actually the carbon based gas that has the strongest impact is actually methane. And so that what radiative forcing refers to is how effective it is at retaining heat in the atmosphere. So you're right, there are others, nitrous oxide, and there are other greenhouse gases, but carbon dioxide is focused on for a number of reasons. But one of them is that it has a strong radiative forcing, a strong impact on the Earth's energy balance, as does methane.
So Claire, Mr. Nate
Thank you.
asks.
That's a lot to look into.
Yeah.
Yeah, thanks, Kat. So Mr. Nate asked a question that I think is probably burning on a lot of people's minds, and that is, how long is it before we get our 54-meter sea level rise?
A long time. A very long time. There is a lot of debate about this in the glaciological community. Another good source for information is the Intergovernmental Panel on Climate Change, where the reports from the Intergovernmental Panel on Climate Change, IPCC, it's an international organization based out of the United Nations. They produce reports that have every several years that have information about the carbon cycle that Kat's asking about, and also glaciological predictions about how much sea level will rise based on glaciological models in the future. And the short answer is I don't know. If I did, I would have a different stature in life. But there are a lot of people working on that question. And so you can think about, okay, if we were to model an ice sheet and how much water it's going to lend to sea level in, let's say, between now and 2100, the variables that you are using to calculate that amount are numerous, and each one carries its own uncertainty. And so, the great thing about science, right? Like there's a lot of disagreement, a lot of back and forth, a lot of discussion. So what are some of those variables? Okay, so obviously, what is the atmosphere going to do, and how is temperature going to change? How will ongoing sea level rise access different submarine basins below ice sheets? And what will the temperature of that water be? How are ocean currents going to be affected? We think about, okay, if you just have an ice sheet and you turn the temperature up, that causes melting. Fair enough. But there are also dynamic changes. So, in addition to just simply turning the heat up for an ice cube, you watch the ice cube get smaller, but you also watch that ice cube sit in a bigger and bigger puddle of water. And that puddle of water affects its friction with whatever surface it's sitting on. And so now not only are you melting more ice, but you're also accelerating its flow out to sea. And so it's a very, very complicated modeling question. A lot of brilliant minds around the world are working on it. I'm not one of them.
Yeah, and it strikes me that that question is particularly hard to. I mean, you can kind of answer questions at the 1 meter level, maybe, but it depends so much on what happens. It's far enough down the line that we just don't know what down the line is going to look like, I would imagine. And I guess the question I always, well, so for instance, I know that there's this kind of doomsday scenario where the West Antarctic ice sheet just slides off of its foundation into the ocean. I don't know what the story on that is now, and I also don't really remember what that does in terms of sea level rise if that were to happen.
It's certainly part of the calculation. So you have not only, so when sea ice melts into the sea, it's not grounded ice, it's already in the ocean. And that does not actually change sea level. So when sea ice melts into the sea, that does not change sea level. What does change sea level is grounded ice on a continent flowing into the sea. That is what has a dramatic impact on sea level. And as you're pointing out, very hard to model and predict, for so many reasons.
Well, okay. So I would like to, let Claire move on to the rest of her day, which includes a drive. And
Can I have one
uh,
more before
yeah,
before
no,
this? Because
so I'm
I have
just
a
saying,
burning
let's
question.
let's have a few more burning questions,
Yeah.
and then
Burning
maybe,
question.
and we can continue talking too if you want.
So again, this is a wonderful occasion to meet you, Claire, and hear firsthand about your research. For some reason, when I was a kid, I got fascinated with Antarctica, and I got my hand on the journals of the original discoverers. So Scott of Antarctica and all these people who went there and spent winters in the early 1900s. And I read all these intimate details about their lives. They tell stories about the loneliness, the way they started behaving less like humans and more like animals because of the loneliness, etc. And my burning question is, how do people go to the bathroom in Antarctica? That's what I want to know.
Oh my
Yes.
goodness.
No, it's a common question.
That's a
W-
logical question.
it's a logical question, yeah.
It's a
Um,
loaded question.
we build a bathroom, uh, and we, depending on where we are, there's a lot of snow, a deep pit, bucket, snow bench with a bench on top of it, ice brick walls or snow brick walls for privacy.
Ice
It's
walls.
yeah, it's quite civilized. It's honestly, it ends up being the least of our concerns, but it's a good question.
I have a former student who participated in the development of the toilet on the International Space Station, which is another place people worry about things like that.
I
Yeah.
just have one final comment question for Claire. When I talked to your dad, I'm going to call him your
Mhm.
dad, John. I sometimes quote Claire's law. Only I didn't have a name for it until today. But Claire's law is data or it didn't happen.
Yeah,
So
fair enough. Yeah,
fair enough, right? Fair enough.
yeah.
So John, Claire's law is going to be imposed regularly,
Yeah,
and
so I'll give Claire the large. So I
Wait,
just want to
wait a
tell you,
minute.
Benjamin. I
Does any
hold on a sec, Sam.
scientist oppose that? Does any scientist say
Well,
Claire's
you
law
know
is
where Benjamin's
invalid?
mind. Let me cut this a little bit short and say, just to let
is right.
Benjamin
I
know,
mean,
I warned
no real scientist would oppose Claire's law.
I warned Claire about you and told her a couple things that you might ask, but I did not feed her. I purposefully did not feed her any responses. I just
This
told
is
her she
true.
might want to think about it.
Yeah, I don't really have
Claire,
any. There's a lot of
you are
great
a saint.
scientists.
You are a saint here. We're going to work on patching things up with John, and a little therapy will take care of it. But you are a saint.
Well,
He's
I've
going to
really
be
enjoyed.
bruised for a while, but
I've really
he'll
enjoyed.
recover. Right? 3 weeks will fix anything.
It's been great to join your group, and yeah, thanks for listening. I hope at least part of it was interesting to you, and happy to be a part of y'all's conversation today. I'm glad you're keeping the scientific discourse going here on Clubhouse, and yeah, it's been a pleasure. So thanks so much.
Claire, stick around.
Thank
I
you
think I'm
very
going to end.
much.
Yeah, thank you so much. That was a wonderful thing. And Claire and Carol's been listening in on my spare phone too,
Oh,
so
good. Okay.
she'll have some things. But I did want to stick around. I'm going to close the room and and I will start an after party room afterwards. I just want to play a couple tunes. I want to repeat one tune and do our usual outro. And yeah, just thanks again, everybody, for coming. This was a particularly wonderful bite of physics, I think.
Thanks, everyone.
So, and we will.